Hello, my name is Brandon Davis, and this is my presentation of my Arduino assignment. In this assignment, we'll cover Part 1, the push button with LED, which will be broken down into the circuit, the code, and a demonstration. Part 2, the potentiometer, which will be broken into the same parts, circuit, code, and demonstration. And then Part 3 was not assigned, but I decided to do it anyway. It's a combination of parts 1 and 2. I will actually only be showing the demonstration. This is the circuit for part 1, the push button LED. On the left hand side you can see the circuit modeled in multisim. In this case the switch was open and you can see that the voltages are all basically zero. On the right side you can see the actual physical circuit I built connected to the Arduino Nano. This slide shows the push button circuit as well. The highlighted portions are what makes up the actual physical circuit, and everything else is actually included inside the Arduino board. This is the code for the push button LED portion. You can see an if-else statement to turn off and on the LED, depending on if the button state is high or low. This is the demonstration for part 1. You can see the code on the computer screen. I'm about to upload it to the Arduino. You can see at the bottom it's verifying the code and then uploading it. Now that it's uploaded, I will demonstrate the functionality of the code. You can see that as I push the button, the LED turns on. When I release the button, the LED turns off. Now I'm opening up the serial monitor. It's hard to see. I'll display the results in a next slide, but you can see ones and zeros. When the button is pushed, it's a 1. When it's not, it's a 0. Now I'm opening up the serial plotter to show the same information graphically. Let's see, we're at 0. I push the button, it moves to 1. I let off, it moves back to 0. Again, I will show this graph in the next slide. These are the results on the left graphically, on the right numerically from part 1, the push button LED. The serial plotter gave us the graph and the serial monitor gave us the numeric output. This is the circuit for part 2, potentiometer. You can see on the right the physical circuit, and on the left you can see a model of the circuit made using multisim. I'd like to point out that line 3 on the multisim circuit is V out from the potentiometer, and the equivalent of that in my physical circuit is the yellow wire seen leaving the page. While the circuit for part 2 was simpler than for part 1, the code was actually more complex. I ended up needing to write 3 different codes in order to completely satisfy the requirements of part 2. This is the code for the raw signal being displayed, as well as the algebraically scaled values being displayed. You can see at the top of my code there's a note directing the user how to choose which value to display. And you can see at the bottom the highlighted section how the raw values are commented out, and the voltage is what would display if this code were to run as is. The small section of code circled in red on the right side of the screen is what it would look like to display the raw values instead of the voltage. As far as the other two versions of this code, we will get to those after the results of this version of the code. This is the demonstration for the code that was just shown. First, we will demo for the raw signal, which will be the actual values being read off of the potentiometer. You can see I'm uploading the code to the Arduino now. Okay, now the code is uploaded. I'm going to open up the serial monitor. And again, it's hard to see the actual numbers in the video, but I can show you the results in the next slide. But you can see that as I rotate the potentiometer, the value does change. Next, I will open up the serial plotter so that I can show the same information graphically. And you can see as I adjust the potentiometer, the value climbs, and then when I start adjusting the other way, the value falls. On this slide are the results from the previous video. On the left, you can see the graph that was created from the raw values from the potentiometer. And on the right side, you can see the list of values generated in the serial plotter. This is the demonstration for the same code, but this time you can actually see I'm changing now from the raw values to the algebraically scaled voltage values, and I'm uploading the code. And this is going to be the same thing. I'm going to open this serial monitor so that we can see the numerical results. And again, as I adjust the potentiometer, the values change. And then I'm going to open up the serial plotter so that we can see the same values on the graph. See, it maxes out at 5 volts and drops all the way down back to 0. These are the results of the algebraic scaling. You have the graph on the left and the numeric values on the right. Notice I do have decimals using the algebraic scaling because I used the float function in my code. And that's also represented in the graph. You can see that the graph can hit basically any value between 0 and 5. And this is the second version of my code for part 2. You can see where it's highlighted. I use the map function to map the values read directly from the potentiometer that range being 0 to 1023, to my voltage range, which is 0 to 5. The next slide will be the demonstration, and then following that will be the results for this particular version of the code. This is the demonstration of version 2 code of part 2, the mapping function. You can see I'm uploading the code. Once the code is uploaded, I will be opening the serial monitor to display the numeric values. And again, you can see the numeric values change as I change the potentiometer. Now I'll open the serial plotter so you can see the graph of those values. Now notice this time the graph makes very sharp jumps as I turn the value. It's actually stopping only at whole numbers because that's the way the map function works. It actually spits out integers, not decimals. Here are the results from version 2 of my code for part 2. As you can see, the graph stops only at whole numbers, and same with the numeric values on the right-hand side. This told me that the map function was not quite as good as algebraic scaling, and this led me to a little more research, which led to my version 3 of this code. Here we have version 3 of my code for part 2. This is what I'm calling the float map version. Upon some research, I found that the map function only works for integers, and I found this function highlighted at the top as a float map function. You can see it adds the float function in front of all of the inputs, and it returns decimals, not just integers. You can see at the bottom where I called the map float function to scale my values from 0 to 5. This is the demonstration for the float map version of the code. You can see I'm uploading the code to the Arduino. And then I will be opening the serial monitor to show the numeric values. And you can see that as I adjust the potentiometer, the values change. Again, it's hard to see in the video. The next slide will have the results. Now I'm opening the serial plotter to show the graphical results. Again, as I change the potentiometer, you can see the output in real time on the graph. Here are the results from the float map version of the code. You can see that we have continuous values where the map function gave us discrete values. This float map version is a lot more similar to the algebraic scaling than just the map function was. Now this was not actually part of the assignment, but I did it anyway just for fun. I took parts of the code from part 1 as well as the code from part 2 and modified it slightly. The value of the potentiometer will actually now create a flashing effect on the LED of the Arduino board. And you can see as I adjust it, it changes the flashing speed. And when I push the button, it's actually a kill switch for the LED. The LED stops flashing when the push button is depressed. And you can see the LED flashes fast or slow depending on how the potentiometer is set. This is just a quick look at the setup I used to record the videos in this presentation. This was the best way I could come up with to get uniform videos and steady camera shots. Thank you for taking the time to watch my presentation.